I want to show you a couple of the calculations that you were to do on the first lab. Some of you struggled with the units on those calculations, and I want to show you how to do those things. The first one is one where you were going to calculate an acceleration, and I used data that was typical of what students had in the lab on this calculation here. So you're calculating the acceleration using this formula, and the distance something traveled was 103.4 centimeters. The time it took was 1.72 seconds. This was an average time. And it's very important that you write down the units whenever you have a number like this so you know what they happen to be. Now here's how you do this calculation. That's the formula. Here's what it looks like with the numbers pushed in. I keep the numbers in the calculation. It's very important that I do that. 1.72 seconds squared. The time is squared, both the number and the units. When I calculate the numerator, I would get 206.8 centimeters. The denominator, I square the 1.72 and I get 2.96. I square the seconds and I get seconds squared. So the units that I have here are the units that I'll end up with. And when I actually do that calculation, I get 69.9 centimeters per second squared. I end up with 3 significant figures because I had 4 significant figures here, 3 significant figures here. I can only keep the lesser of the 2 numbers of significant figures on division, so that's what I end up with. So by keeping track of the units all the way through, I end up with correct units for an acceleration. Later in the lab, you dropped pieces of paper and used that to calculate your reaction time using this formula here. Typical student distance when you calculate the average distance might have been 14.7 centimeters. And for this calculation, I had you use an acceleration due to gravity of 980 centimeters per second squared. So let's see how you do this calculation and why you should end up with a time at the end. So t is equal to the square root of 2 times the distance there, 14.7 centimeters, divided by g, 980 centimeters per second squared. Now, underneath that square root, I'll show you what happens to the units. Keep in mind this is under a square root. You've got centimeters on top and centimeters per second squared on the bottom. When you divide by a fraction, you invert it and multiply, so this becomes centimeters times seconds squared over centimeters. And when you multiply a single number by a fraction, it multiplies by the numerator. So this centimeters is up in the numerator, and it'll divide with the centimeters in the denominator. And under the square root, you end up with units of seconds squared. And so what you'll actually have here now, now that I've simplified the units, I can write this as, let's see, this would be 29.2 centimeters. Whoops, not centimeters anymore. I solved for those things. 980. And the units that are under here now have been simplified to seconds squared. When you take a square root of seconds squared, you end up with seconds. When you do the arithmetic on this, you would end up with 0.17 seconds. So I wrote down all the units here. I wrote down the simplified units there that I got by going through this little analysis. And then when I'm done, I have that. I have only 2 significant figures here because the 980 is only good to 2 significant figures. So those were the calculations in Lab 1, the way that you should have done them. by keeping track of units.